Modern astrophysics is struggling with three massive, unresolved numerical discrepancies: dark energy, the vacuum catastrophe, and the Hubble tension. To put the scale of these problems in perspective, we are currently missing 69% of the universe's energy. A standard quantum calculation for the vacuum of space is off by a factor of 10 to the 120th power, and local measurements for how fast the universe expands refuse to match early cosmos measurements. For decades, the standard approach to fixing these holes has been hunting down invisible dark fluids and exotic particles hiding in the vastness of space. But the math points to a different possibility. We might simply be measuring the wrong dimension. Resolving these anomalies requires stepping away from the three-dimensional volume of space and looking strictly at its two-dimensional boundaries. The surface of our own sun, the exact 2D photosphere where light decouples from matter, is the ultimate local test case for a radiative boundary. Physicists use a boundary invariant equation to calculate the balance between escaping heat and inward gravity. Applying standard physical laws, mass and gravity cancel each other out. The remainder evaluates to a strict geometric constant, pi cubed over 15, or roughly 2.0671. We can test if this mathematical quirk is a physical reality using strictly independent measurements. When we run the sun's direct orbital mass, radius, and radiometry through the equation, we get an empirical result of 2.0599, nearly an exact match for the geometric limit. To confirm this isn't a fluke, we can look at an independent sample of 190 different binary stars. Across stellar masses ranging from a fraction of our sun to 30 times its size, the data clusters at this same mathematical limit. At any stable physical boundary, the internal mass becomes mathematically irrelevant. What is left is purely a two-dimensional geometric capacity. Since this geometric boundary number holds true for local stars, we can project it outward to the absolute vacuum edge of the cosmic horizon. We apply that identical capacity, pi cubed over 15, to cosmological parameters defining the observable universe. Mapping this 2D surface into a 3D volume introduces an area-to-volume ratio of 1:3. This divides our constant, yielding 0.689, the exact fraction of dark energy. Dark energy emerges here as the passive mathematical tension inherent to the horizon's 2D boundary. This identical boundary logic explains the vacuum catastrophe. The discrepancy arises because quantum physicists calculate vacuum energy as if it were an active, three-dimensional volume, but a boundary is flat. If we compress that expanding three-dimensional vacuum into a two-dimensional horizon grid, it must be tiled by discrete Planck area pixels. The mismatch of 10 to the 120th power represents the macroscopic to microscopic area scaling factor required to tile the boundary. That leaves the Hubble tension. Measurements of the early universe's continuous fluid show one expansion rate, while the clumpy, void-filled web of the modern universe shows a faster one. Geometry's kissing number dictates 12 spheres surrounding a central sphere leave unavoidable empty gaps. Transitioning to a discrete network, the universe stretched to fit these 12 gaps. This stretching adds 1/12 to the expansion rate. Multiplying the early universe's 67.4 by 13 over 12 yields exactly 73. The Hubble tension becomes a predictable consequence of 3D topological packing geometry. A single 2D normalization rule, validated on the surface of our sun, mathematically maps the fraction of dark energy, accounts for the vacuum catastrophe, and derives the local Hubble expansion rate. It demonstrates that the universe operates holographically on macroscopic scales, bypassing the need to invent unobserved phantom particles or rewrite physics. Generations of astrophysicists have searched for complex answers hidden deep inside the three-dimensional volume of space. But the math suggests the universe is defined by its boundaries. The solutions to our biggest cosmic mysteries are written directly on the surface.